So when we train a multi-layer perceptron or any deep learning model for that, we should monitor the gradients, because the most important part of any optimization strategy, right, is about gradients. The whole game is about gradients, because gradients are what we use to update our weights, right? To update our weights, we basically use gradients. So let's assume you have a neural network like this, where this is your input layer, right? You have a bunch of inputs here like xi1, xi2, so on and so forth, right? And you have your, let's say, layer 1, okay? And this is fully connected, right? When I write this, what I mean here is this is a fully connected layer. Let's assume I might have a bunch of neurons here, right? Then layer 2, again this is also fully connected, right? Layer 2, and then I have my output layer. Let's say this is my output layer, right? So given an input, my output is basically yi hat, right? Given an xi. So given an xi as my input, this is my model, let's say. So what you should look at is, and there are a bunch of weights here, right? All of your W1 is here, your W2s are here, and W3s are here, right? So the suggestion here is, when you monitor, what I mean by gradient monitoring here is, it's a good habit. It's a good habit to monitor your gradients, for each weight, your gradients and updates, right? And the whole update, what I mean by update here is, so you have your wt equals to wt minus 1 minus something, right? This could be complex based on the algorithm you are using. If you're using a very simple very simple SGD, okay, mini batch SGD, you just have GT. But if you could have complex variation, so this whole term is the update, because this is what you're using. If you're using AdaGrad and other stuff, it's slightly more complex. But in a nutshell, you're changing your WT minus 1 to WT using this update, right? So you should always monitor your gradients and updates. And you should monitor it for each epoch. For each epoch, you should monitor it. And also you should monitor it for each weight, for each epoch, for each weight, and for each layer, right? Because we know that, say, imagine why this monitoring is useful. This monitoring is very useful to detect problems like vanishing gradient, right? To detect problems like vanishing gradients, right? To detect problems like vanishing gradients, very useful. And vanishing gradient happens more often in the early layers, right? Because what happens, the weights that are here, for the final loss function, right? For the whole weight to back propagate, right? Because there are lots of multiplications of derivatives, all of them less than 1, right? So you might end up with a vanishing gradient problem for weights in this region, and not so much in weights here. And hence you should always monitor your gradients and the whole update itself. This whole term, which we call as update term, for each epoch you should monitor it, for each weight you should monitor it, and you should also monitor it for every layer. And when gradients become too small, especially in the first few layers, that could indicate that you have a vanishing gradient problem, right? And if the gradient becomes very large, right? If the gradients become very large, you could be running into the exploding gradient problem. You could be running into the exploding gradient problem when the gradient becomes very large. And when you have, because you have to monitor this to understand what is happening. If you detect a vanishing gradient problem, you should immediately change your activation functions to ReLU if you are using something like sigmoid or tanh, right? And gradient clipping is a very interesting idea, which is used to avoid or to get rid ourselves of the exploding gradient problem. So the solution to the exploding gradient problem is gradient clipping, right? And the gradient clipping is a very, very simple and elegant solution, right? So imagine I have lots of weights. Remember, I have all of my weights, right? I have lots of weights. If I place all of my weights in a single vector, okay, let me call it as capital W, right? Capital W is basically all the weights in my network, right? All the weights that I have in my network. So the idea here, when you want to perform gradient clipping, the core idea is this, right? If you think of this as a vector, right? Your weight as a vector, you can also think of your gradients as a vector. Right? You can also think of your gradients as a vector. Probably in this, you have derivative of L with respect to derivative of 1, 1, 1. Here you have derivative of L with respect to derivative 1, 2, 2. Right? 1, 2, 3, so on and so forth. Right? You can think of it as a gradient vector. Let's call this gradient vector as capital G. Okay. So if you have an exploding gradient problem, one way, suppose I have one of these gradients which is very large. Let's say 200 as a gradient here, or I may have one let's say derivative of L with respect to W321 is, let's say, 1000. It's becoming very, very large, right? So when you have a gradient which is very large, right, one thing that we can do is gradient clipping, and the concept is very simple. The concept is the new gradient vector is take the regular gradient vector that you get divided by the norm, the L2 norm of the vector, and multiply it by some threshold. Okay, this tau here is a threshold. The symbol in Greek is called tau. Okay, it's called threshold. And this is L2. This is the L2 norm. This is the 2 norm. Okay, and this gradient clipping strategy is called L2 norm clipping. Now, when I have a vector G, let's assume I have a vector G here. Okay, let's assume I have 2, 5, 10, 1000, and 0.5. Right? The norm of when I divide G with norm of G, right? What I get here literally is all these values, all these gradients, all these individual gradients will be less than 1. Because the norm of G is greater than all of these things. Right? This is the L2 norm. And we know what L2 norm is. Sum of squares of each of this term and square root. Okay, what is L2 norm? G1 square plus G2 square plus G3 square, so on and so forth, and under root of this. Right? While this is the G1, this is G2, this is G3, this is G4. We take each of the components, square them up, and under root. This is your L2 norm of G. This is your 2 norm of G, right? And since you're squaring all of them and taking the under root, the L2 norm of G is greater than each of these individual terms. And when I divide each of these terms with the norm of G, the L2 norm of G, each of these values is going to be less than 1. And then I'm multiplying it with the threshold tau. Suppose if I decide my tau is equal to 2, let's just say, then finally in my G nu, all of my gradients in my G nu vector are less than tau, less than equal to tau, right? So this is called L2 norm clipping. Because what are we doing here? We are using the L2 norm and we are using tau to clip, to basically say all gradients have to be less than equal to tau. And we're using the L2 norm to enable that, and hence it's called L2 norm clipping. And this is readily available in most libraries. So wherever you have exploding gradient problem, the simplest way, there are other strategies also, the simplest way is your L2 norm clipping strategy. To ensure that none of your gradients are too large. Very, very simple thing. But as a rule of thumb, always monitor your gradients and keep looking for what's happening. You should monitor your gradients and also updates to see if you're running into vanishing gradient problem or exploding gradient problem or some other problem. Okay, this is important to debug. Otherwise, you can get lost. You might be training an algorithm, it is not converging, it's not working. You can bang your head for days together. So very, very important practical strategy is to monitor gradients. We'll see how to do it programmatically in the next chapter when we learn TensorFlow in more detail.